What if everything we thought we knew about the birth of the universe was just a fraction of the truth? Picture this, the moment of creation, not as a violent explosion, but as a mysterious, radiant emergence from the depths of something far stranger than the Big Bang. Today, we're diving into one of the most mind-bending ideas in modern cosmology, the possibility that our universe wasn't born from a bang at all, but from a white hole, a cosmic phenomenon so bizarre, it flips our understanding of reality on its head. Imagine a place where time runs backward, where matter and energy don't collapse but burst forth, where the very fabric of space-time behaves in ways that defy logic. This isn't science fiction, it's a theory gaining traction among some of the most daring minds in physics. For decades, the Big Bang has been the cornerstone of cosmology, the story we tell about how everything began. But what if that story is incomplete? White holes, often called the twins of black holes, are theorized to be regions where matter and energy can only escape, never be absorbed. Think of a black hole in reverse. Instead of pulling everything in, a white hole pushes everything out. Now, stretch that idea to the scale of the entire universe. Could our cosmos be the result of a white hole's explosive birth? The implications are staggering. It would mean the Big Bang wasn't the beginning but a moment in a much larger, more mysterious cycle, a cosmic heartbeat, pulsing between creation and destruction. This idea doesn't just challenge textbooks, it rewrites them. If white holes are real, they could explain some of the universe's deepest puzzles, from the nature of dark energy to the origins of time itself. But here's the catch: no one has ever seen a white hole. They exist for now only in equations and the imaginations of physicists brave enough to question the status quo. So why should we care? Because this isn't just about astronomy, it's about redefining what's possible. It's about peering into the unknown and asking, what if? The same question that has driven every great leap in human understanding. Strap in, because we're about to explore a theory that could change how you see the universe and your place in it forever. The Big Bang Theory has long been the bedrock of our cosmic origin story, painting a picture of an infinitely dense, scorching hot singularity that suddenly expanded, giving birth to space, time, and everything we know. According to this model, the universe began as an unfathomably tiny point roughly 13.8 billion years ago, then exploded outward in a fiery burst of energy that's still stretching the cosmos today. We see evidence of this in the cosmic microwave background, the faint afterglow of that primordial heat, and in the way galaxies continue racing away from each other as if propelled by that ancient momentum. But for all its explanatory power, the Big Bang leaves some glaring gaps. Take the singularity itself, the so-called starting point of everything. Physics simply breaks down when we try to describe it. Gravity becomes infinite, the laws of quantum mechanics and relativity clash, and the question of what came before is met with silence. Even the expansion of the universe raises eyebrows. Why was the initial push so perfectly balanced that galaxies formed instead of matter scattering into emptiness? And what exactly triggered the bang in the first place? These puzzles hint that our universe's origin might be more nuanced, and that's where white holes enter the conversation. Imagine rewinding a black hole's behavior. Instead of crushing matter into oblivion, a white hole would theoretically spit it out with relentless force like a cosmic fountain. Now apply that to the Big Bang singularity. Could it have been the eruption of a white hole, an event where space-time itself burst into existence from some other realm? This twist doesn't just dodge the infinity problem. It suggests our universe might be one piece of a larger puzzle, born from a phenomenon we're only beginning to imagine. The Big Bang isn't wrong per se, it just might be part of a grander, stranger story. So what exactly is a white hole? At its core, it's a hypothetical mirror image of a black hole, where the rules of cosmic behavior flip entirely. While a black hole acts like a one-way door for matter and energy, trapping everything that crosses its event horizon, a white hole would be its exact opposite, a region of space where nothing can enter but everything must exit. Picture a black hole as a cosmic drain, sucking everything into its depths with irresistible force. Now reverse that image. Instead of a drain, think of a fountain, endlessly gushing out matter and energy into the universe. That's the essence of a white hole, not a devourer but an expeller. The concept didn't come out of thin air. These bizarre objects emerged naturally from Einstein's field equations, the same mathematical framework that predicted black holes over a century ago. In fact, the equations don't distinguish between the two. They simply describe a curvature of space-time so extreme that it could collapse inward or erupt outward. For decades, physicists dismissed white holes as mathematical quirks, assuming nature would favor black holes while leaving their hypothetical twins to the realm of theory. But as we've dug deeper into the mysteries of the cosmos, the idea has resurfaced with new relevance. Could these cosmic fountains actually exist? Here's where it gets even stranger. If white holes are real, they'd behave in ways that defy our everyday intuition. Time itself would appear to run backward from an outside observer's perspective, like watching a movie in reverse. Matter wouldn't just emerge, it would explode outward with unimaginable energy, as if the universe itself were being born anew. Some theories even suggest that a white hole's eruption could mimic the conditions of the Big Bang, raising the tantalizing possibility that our entire universe might be the product of one. Yet for all their theoretical elegance, white holes face a glaring problem. We've never detected one. They violate the second law of thermodynamics, which states that entropy, the universe's tendency toward disorder, must always increase. A white hole spewing out organized energy seems to break that rule. So why do physicists still entertain the idea? Because white holes could solve puzzles that black holes alone can't. Take the information paradox, the question of what happens to the data swallowed by a black hole. If black holes eventually evaporate, as Stephen Hawking proposed, where does that information go? One radical solution suggests it might re-emerge through a white hole, preserving the universe's quantum rulebook. Others speculate that white holes could be the secret engines behind gamma-ray bursts, the most violent explosions in the cosmos. And then there's the wildest idea of all, that every black hole in our universe might birth a new one through a white hole, creating a hidden network of baby universes. Whether white holes are real or just mathematical phantoms, their role in physics is undeniable. They force us to confront the limits of our understanding, to question whether the universe plays by the rules we've written, or if it's hiding a far stranger set of possibilities. After all, if Einstein's equations allow for white holes, who's to say nature hasn't found a way to make them? The hunt for answers isn't just about filling textbooks, it's about discovering whether reality is even more wondrous than we've dared to dream. The math behind white holes isn't just speculative, it's rooted in the same equations that define black holes and the fabric of space-time itself. When Einstein formulated his theory of general relativity, he unwittingly opened the door to these cosmic oddities. The equations describe a singularity, a point where gravity becomes infinite, but they don't care whether that singularity pulls matter in or pushes it out. That symmetry led physicists like Rovelli and Bojowald to ask, if black holes exist, why not their mirror images? Rovelli's work in loop quantum gravity, a framework aiming to reconcile relativity with quantum mechanics, suggests something astonishing. When a black hole reaches the end of its life, it might not simply vanish. Instead, quantum effects could cause it to rebound, not as another black hole, but as a white hole. Picture a collapsing star squeezing down to an unimaginable density, then hitting a quantum bounce like a compressed spring recoiling. The result, a violent ejection of all the matter and energy the black hole once consumed. This isn't just poetic imagery, it's a prediction arising from the math of spacetime's granular structure at the smallest scales. Loop quantum cosmology, a related theory championed by Bojowald, takes this idea even further. It proposes that the Big Bang singularity itself could have been the aftermath of a white hole's birth in some previous universe. In this model, the universe doesn't start with a bang but with a bounce, a transition from contraction to expansion, bypassing the infinities that plague classical physics. The equations show space-time as a woven tapestry of tiny loops, discrete and finite, which can't collapse to a true singularity. Instead, they reach a maximum curvature and rebound, turning a black hole's collapse into a white hole's explosion. This isn't just theoretical sleight of hand. These models solve real headaches in physics. For instance, they sidestep the information paradox by suggesting black holes don't destroy information, they eventually spit it back out. They also offer a way to unify quantum mechanics and gravity without inventing new laws of physics. But the most mind-bending implication, our universe might not be the first or the last. If white holes can birth new space-times, then cosmic history could be an endless cycle of collapses and rebirths, with each black hole in our cosmos potentially seeding another. Yet the challenge remains, how do we test these ideas? White holes, if they exist, would be astonishingly rare or short-lived, vanishing in a flash of radiation. Some researchers speculate that certain gamma-ray bursts or fast radio bursts could be white hole signatures, cosmic fireworks signaling their existence. Others argue that quantum gravity's effects might leave faint imprints in the cosmic microwave background, like echoes from a previous universe. Until we detect such clues, white holes remain tantalizing what-ifs at the edge of science. But that's the beauty of theoretical physics. It lets us explore the universe not just as it is, but as it might be. And sometimes the wildest ideas turn out to be true. If our universe is the interior of a white hole, it would rewrite not just the story of our cosmic origins, but the very nature of reality itself. Think of it like this: instead of the Big Bang being a singular, inexplicable starting point, it could be the moment a black hole from some other universe collapsed to its limit, and then rebounded as a white hole, birthing our cosmos in the process. This idea, sometimes called the white hole universe hypothesis, flips the script entirely. The singularity, that infinitely dense, infinitely hot point we've always associated with the Big Bang, wouldn't be the beginning but a transition. A cosmic pivot where the crushing grip of a dying black hole gives way to an explosive rebirth. This vision shares striking parallels with the Big Bounce theory, which suggests the universe cycles through periods of expansion and contraction, collapsing into a dense state before bouncing back out again. But here's the twist: the white hole hypothesis takes that idea even further. It proposes that each bounce isn't just a reset of our own universe, but a handoff between separate cosmic realms. Imagine a black hole in some parent universe collapsing so violently that its core doesn't just crunch, it flips inside out, becoming a white hole that becomes an entirely new universe. In this scenario, our entire cosmos could be the other side of a black hole's demise, with the Big Bang marking the moment that transformation went critical. What's fascinating is how neatly this solves one of the biggest headaches in cosmology, the singularity problem. In traditional Big Bang physics, everything emerges from a point where the laws of physics break down, a mathematical dead end. But if the Big Bang was actually a white hole's eruption, there's no true singularity. Instead, quantum effects would prevent infinite collapse, creating a cosmic rebound. Picture a ball bouncing off a floor. It doesn't vanish when it hits the ground, it changes direction. In the same way, a collapsing black hole might hit a quantum floor, reversing its collapse into an explosion. This isn't just poetic speculation. The math behind loop quantum gravity, a leading theory attempting to unite quantum mechanics and relativity, actually predicts such a bounce. Tiny, discrete units of space-time would act like a safety net, stopping the infinite crush of gravity and triggering a rebound. The result: no singularity, no breakdown of physics, just a transition from implosion to explosion. And if that's true, it means our universe didn't emerge from nothingness, but from the transformation of something else. The implications are staggering. If white holes can birth universes, then black holes might be cosmic seeds, each carrying the potential to create entirely new realities. Our universe could be one branch on an infinite tree of cosmic generations, with every black hole inside it spawning its own offshoot universe. And here's the kicker: this would mean the laws of physics in our cosmos, the constants that seem so finely tuned for life, might not be arbitrary at all. They could be inheritances shaped by the physics of whatever universe birthed ours. Of course, this raises questions we're only beginning to grapple with. If our universe came from a white hole, what does that say about the parent universe? Could we ever detect traces of it? Some theories suggest subtle fingerprints might linger in the cosmic microwave background or the distribution of dark matter. Others propose that black holes in our universe could one day spawn their own white holes, continuing the cycle. But for now, these ideas lie at the edge of science, part math, part imagination, and wholly transformative. What's certain is this: if the white hole hypothesis holds any truth, it means we're not just living in a universe with black holes, we might be living inside one. The search for white holes isn't just a theoretical exercise. It's a cosmic detective story with clues hiding in plain sight. Take the cosmic microwave background, that ancient echo of the Big Bang. While it's mostly uniform, there are strange, unexplained anomalies, cold spots, asymmetries, and patterns that don't quite fit the standard model. Some physicists, like Nikodem Poplawski, have suggested these irregularities could be scars from a white hole's explosive birth. Imagine a fingerprint pressed into the fabric of space-time, a remnant of some violent transition from a parent universe to ours. If true, these subtle wrinkles in the SIMB might be the closest thing we have to a cosmic birth certificate. Then there's the mystery of gamma-ray bursts, the most energetic explosions in the universe. Typically, they're linked to collapsing stars or colliding neutron stars. But a handful defy explanation, erupting with energies and durations that don't match known astrophysical processes. Could these outliers be white holes briefly flickering into existence? In 2012, physicists Alon Retter and Shlomo Heller proposed just that, arguing that certain short, intense bursts might align with the predicted signatures of a white hole's final, violent ejection of matter. Picture a cosmic geyser blasting out a lifetime's worth of energy in seconds before vanishing forever. The challenge: these events are so fleeting, so rare, that catching one would be like spotting a lightning bolt in a thunderstorm from a million miles away. Even black holes might hold clues. Some models suggest that when a black hole dies, it doesn't fade quietly, it transforms. Loop quantum gravity predicts a quantum bounce, where a collapsing black hole rebounds as a white hole in its final moments. If this happens, the resulting explosion would release energy comparable to a supernova, packed into a fraction of the time. The trick is distinguishing such an event from the usual cosmic fireworks. Researchers like Rovelli speculate that future telescopes, tuned to specific high-energy frequencies, might spot these telltale flashes, cosmic Morse code signaling a black hole's rebirth on the other side of spacetime. But why is the evidence so elusive? White holes, if they exist, would be incredibly unstable. Unlike black holes, which persist for eons, a white hole's nature, spewing out matter and energy, means it would likely burn out fast, like a firework dissolving into smoke. Plus, their theoretical defiance of entropy makes them statistical unicorns. The universe tends toward chaos, not orderly eruptions. Yet, as physicist Sean Carroll points out, the laws of physics don't outright forbid them, they just make them vanishingly unlikely. That's why scientists aren't searching for white holes in isolation. Instead, they're looking for their shadows, anomalies in data, unexpected energy spikes, or distortions in space-time that hint at something stranger lurking beneath the math. The hunt is also moving beyond pure observation. Advanced simulations like those run by the Perimeter Institute are testing how white holes might behave in the wild. One startling finding: under certain quantum conditions, a white hole's explosion could mimic the early universe's expansion, complete with a flood of particles and radiation. If simulations can reliably match real cosmic events, we might finally have a roadmap to spotting these phantoms. Meanwhile, projects like the James Webb Space Telescope and next-gen gravitational wave detectors could provide the precision needed to catch a white hole's whisper in the cosmic noise. What's at stake isn't just confirming an exotic theory. If white holes are real, they'd reshape our understanding of causality, entropy, and the very arrow of time. They'd prove that universes can be born not from nothingness but from transformation, that every ending might be a beginning in disguise, and that's the ultimate allure, the chance to rewrite the universe's origin story, not as a solitary event, but as one link in an endless chain of cosmic rebirth. Until then, every anomaly, every unexplained burst of energy is a tantalizing maybe, a flicker of possibility in the dark. For all the elegance of white hole theories, they come with a glaring problem. The universe doesn't seem to play by their rules. The second law of thermodynamics, a cornerstone of physics, states that entropy or disorder must always increase over time. White holes, by their very nature, defy this. Imagine a cosmic spill reversing itself, with scattered particles snapping back into place like a rewound film. That's essentially what a white hole would do: eject organized energy into the universe, seemingly reducing entropy instead of increasing it. To skeptics, this isn't just unlikely, it's physics blasphemy. As astrophysicist Ethan Siegel puts it, the universe doesn't do undo. Then there's the elephant in the room: no one has ever seen a white hole. In science, evidence is king, and decades of searching have turned up zero conclusive signatures. Detractors argue that if white holes existed, even fleetingly, we'd expect to spot their explosive aftermath, gamma-ray bursts with peculiar energy profiles or unexplained ripples in spacetime. Yet every candidate so far has had a more mundane explanation. This absence of proof isn't just inconvenient. It fuels the criticism that white holes are mathematical phantoms, elegant on paper but absent in reality. Even the math has its pitfalls. Some solutions in general relativity that describe white holes assume perfect, idealized conditions: no external matter, no quantum fluctuations, no messy astrophysical realities. Introduce even slight disturbances, and these models can collapse like a house of cards. French physicist Thibault Damer demonstrated that white holes might be inherently unstable, collapsing into black holes the moment they form. Think of trying to balance a pencil perfectly on its tip. The slightest breeze topples it. If Damer is right, white holes might be equally ephemeral, existing for mere instants before nature corrects the imbalance. But perhaps the sharpest criticism is that white holes don't actually solve problems, they relocate them. Take the Big Bang's singularity. Proposing a white hole origin swaps one mystery, an inexplicable starting point, for another, an unexplained parent universe. It's like explaining a magic trick by invoking a second, even more baffling trick. As philosopher of science Karl Popper warned, a theory that can't be falsified isn't science, it's metaphysics. Without observable predictions or testable differences from standard cosmology, white holes risk drifting into the realm of untestable speculation. Yet defenders counter that dismissing white holes outright might be premature. After all, black holes were once deemed mathematical oddities before technology caught up with theory. The same could hold here. Quantum gravity models, like loop quantum cosmology, provide mechanisms where white holes emerge naturally from black hole evolution, no entropy violations required. In these frameworks, the bounce isn't a reversal of time but a quantum reset, like a computer rebooting. The disorder isn't erased, it's repurposed. As for observational evidence, proponents argue we've been looking for the wrong things. Instead of giant cosmic geysers, white holes might manifest as subtle quantum tremors or anomalies in gravitational wave data signatures we're only now developing tools to detect. The debate crystallizes a deeper tension in physics. How far should we trust math as a guide to reality? Einstein's equations birthed white holes just as surely as they predicted black holes. If we discard one prediction because it feels unnatural, do we undermine the other? Or is science's job to follow the evidence even when it leads somewhere unsettling? What's clear is that white holes force us to grapple with the boundaries of our knowledge. They might remain speculative, but in that speculation lies progress. Every revolutionary idea in science, from plate tectonics to dark matter, faced skepticism before proof. Whether white holes join that pantheon or fade into obscurity, their real value might be in the questions they force us to ask. After all, the universe isn't obligated to make sense to us. Sometimes the strangest ideas are the ones that crack reality wide open. The white hole hypothesis isn't the only game in town when it comes to reimagining the Big Bang. Cosmic history has no shortage of daring theories, each offering its own twist on how everything began. Take the cyclic universe model, which suggests our cosmos is stuck in an endless loop of expansion and contraction, a cosmic accordion breathing in and out across eons. While this idea elegantly sidesteps the need for a definitive starting point, it struggles to explain why each bounce wouldn't gradually sap the universe's energy, leaving later cycles colder and emptier. White holes offer a compelling counterpoint. Rather than recycling the same universe, they propose a generative mechanism where each black hole's collapse could seed an entirely new cosmos, preserving energy through transformation rather than repetition. Then there's the holographic principle, which posits that our three-dimensional reality might be a projection from a two-dimensional surface at the universe's edge, like a cosmic version of a shadow puppet show. This mind-bending idea solves certain quantum gravity puzzles by treating space-time as an information-rich boundary. But where holography focuses on how the universe encodes data, the white hole hypothesis tackles something more visceral, the origin of the universe's raw materials. Imagine combining the two. If a white hole's explosive birth created our cosmos, its event horizon could theoretically serve as the holographic screen, with every particle in our universe tracing back to information imprinted during that primordial eruption. Multiverse theories take a different approach, suggesting our Big Bang was just one bubble in an infinite froth of universes, each with its own laws of physics. While this explains why our universe seems oddly fine-tuned for life, we just happen to be in the bubble where conditions are right. It does little to clarify what triggered our specific bubble's inflation. White holes inject a potential mechanism here. If each black hole in a parent universe spawns a white hole elsewhere, then multiverses wouldn't just float randomly. They'd be connected by cosmic umbilical cords, with black holes acting as tunnels between realities. This could even explain dark energy's mysterious acceleration of the universe's expansion. Some physicists speculate that what we call dark energy might be residual radiation from our white hole's birth, a kind of cosmic exhaust still pushing space-time outward from that initial explosion. What sets the white hole hypothesis apart is its ability to weave these disparate threads into a single narrative. Unlike string theories, hidden dimensions, or the quantum fluctuations of vacuum genesis models, white holes emerge from straightforward extensions of Einstein's equations, no extra dimensions or untested physics required. They also provide something rare in cosmology, a testable legacy. If our universe is a white hole's aftermath, its explosive birth might have left detectable scars in the distribution of galaxies or the polarization of ancient light. Other theories rely on phenomena forever outside our observational reach, like parallel universes or pre-Big Bang geometries, yet these ideas aren't mutually exclusive. The most radical possibility that multiple theories could be simultaneously true. A white hole might birth a universe that later joins a multiverse network, or a holographic boundary could form during the quantum bounce that creates one. This isn't just theoretical mashup, it's a recognition that the universe's origins might be too complex for any single framework to capture alone. While white holes offer a compelling answer to the how of cosmic birth, they leave the why wide open. That's where science and philosophy start to blur, reminding us that every origin story, no matter how rigorous, still grapples with the ultimate mystery, why there's something rather than nothing. And perhaps that's the most profound lesson of all, not just about white holes, but about the limits of human understanding when facing the infinite. If our universe truly began as a white hole's explosive birth, it doesn't just rewrite the past, it reshapes the future. Suddenly, the cosmic endpoint isn't a cold, dark fade into oblivion, but a potential rebirth. Picture this: every black hole in our cosmos, from the tiny primordial ones to the supermassive monsters at galaxy centers, might not be dead ends. They could be cosmic incubators, each collapsing to a point where quantum physics takes over, triggering a bounce that flips them inside out. Instead of a big crunch where everything collapses, we'd have countless little bangs, spawning new universes like bubbles in an infinite cosmic foam. This vision turns the traditional heat-death scenario on its head. Normally, we assume the universe will keep expanding forever, stars burning out until only black holes remain, slowly evaporating over trillions of years. But if white holes are real, those evaporating black holes might have a surprise finale, a violent rebirth as new space-times. The universe wouldn't just end, it would fragment into countless offspring, each with its own laws of physics, its own arrow of time. Some might collapse instantly, others expand forever, creating a Darwinian selection of cosmic landscapes where only the fittest universes, those with stable constants, persist long enough to birth others. The implications ripple farther. If white holes bridge universes, they might function as natural wormholes, not just in space but across realities. Einstein's equations already allow for such tunnels, Einstein-Rosen bridges, but they're usually considered unstable, pinching shut before anything could pass through. A white hole's quantum bounce could change that. Imagine a black hole in our universe collapsing into a white hole elsewhere, creating a transient bridge between worlds. Traveling through it would still be impossible. The forces would rip anything apart, but information might bleed through. That could explain bizarre quantum phenomena like entanglement, where particles instantly influence each other across vast distances. Maybe they're not communicating faster than light, maybe they're linked through a microscopic white hole's echo. Yet for all its elegance, this idea raises thorny questions. If universes can be born from white holes, what determines their properties? Do they inherit physics from their parent, or is each bounce a random reset? Some theories suggest quantum fluctuations during the bounce could tweak fundamental constants, meaning every new universe might have slightly different rules. That could explain why ours seems so finely tuned for life. We're just one iteration in a vast multiverse where most versions lack the right conditions. Others propose that information from the parent universe leaks through, leaving faint imprints like cosmic DNA. The biggest mystery, whether time itself would flow the same way in these sibling universes. From our perspective, a white hole's eruption looks like a big bang, a beginning, but from the parent universe's view, it might be a black hole's death through an ending. This duality hints that before and after could be illusions, dependent on which side of the singularity you're standing. If true, our universe's birth wasn't the first chapter but a page torn from another story, it's passed forever, locked behind an event horizon we can't peer beyond. What's thrilling is that these aren't just thought experiments. future telescopes could hunt for anomalies in the cosmic microwave background, subtle swirls or temperature patterns that betray a pre-Big Bang structure. Gravitational wave detectors might catch echoes from black hole mergers, whispers of extra dimensions or quantum fuzziness that hint at a bounce. Even tabletop experiments with ultra-cold atoms could simulate white hole dynamics, testing how quantum information survives extreme conditions. The white hole hypothesis doesn't just offer a new ending to our cosmic tale. It suggests the story might not have an ending at all, just infinite beginnings, each rewriting what we thought was possible. And that's the most profound shift of all, realizing that the universe's fate isn't written in stone, but in the unstable, shimmering potential of singularities waiting to turn inside out. Imagine harnessing the energy of a white hole, an endless cosmic fountain spewing out matter and radiation at unfathomable scales. If this theory holds, it wouldn't just rewrite astrophysics textbooks, it could redefine humanity's future in space. Traditional propulsion systems, limited by fuel and the tyranny of distance, would pale next to the possibility of tapping into white hole dynamics. Picture a spacecraft drawing power from miniature, lab-generated white holes, a concept already toyed with in quantum experiments. These wouldn't be the universe birthing giants of cosmology, but controlled, micro-scale eruptions, offering energy densities that make nuclear fusion look like a campfire. The challenges are monumental. Containing such forces without triggering catastrophic chain reactions tops the list, but the payoff could be interstellar travel powered by the very mechanisms that might have birthed our cosmos. Philosophically, the implications cut even deeper. If our universe is the interior of a white hole, what or who exists beyond its event horizon? Causality, the bedrock of reality as we know it, unravels at this edge. From our perspective, time flows forward from the Big Bang, but to an observer outside, our entire history might appear reversed, like watching a film reel in rewind. This flips existential questions on their heads. Is free will an illusion if our past is someone else's future? Are the laws of physics in our universe just local bylaws, shaped by the conditions of the white hole that birthed us? The theory blurs the line between science and metaphysics, suggesting that what we call nature might be the quirks of a very specific cosmic womb. Then there's the unsettling notion of cosmic isolation. A white hole's event horizon is a one-way exit. Nothing external can enter. If we're inside one, it means we're fundamentally cut off from any parent universe that spawned us, forever trapped in a reality with no accessible outside. This raises haunting parallels to simulation theory, where our universe could be a self-contained experiment running in some higher dimensional computer. But here, the programmer isn't an alien technocracy. It's the brute mechanics of black hole physics in another reality. The difference, simulation theory, is untestable speculation. White holes, at least in principle, leave fingerprints, anomalies in quantum gravity or space-time geometry that future experiments might detect. The most profound shift might be in how we perceive existence itself. If black holes in our universe spawn white holes elsewhere, then creation isn't a singular event but an ongoing process, with every collapsing star potentially igniting a new cosmos. We're no longer just inhabitants of a universe, we're participants in a grand, self-replicating chain of realities. This reframes humanity's role from cosmic accident to unlikely witnesses of a fractal multiverse, where life emerges not despite the universe's indifference but because its very structure allows infinite tries. Yet for all its grandeur, the theory leaves us with humbling uncertainties. If white holes bridge universes, could information, a message, a memory, even consciousness ever traverse the divide? Or are we forever locked in our pocket of space-time, left to wonder what lies beyond the veil of the Big Bang's afterglow? These aren't just scientific questions. They're the echoes of an ancient human urge to find our place in the tapestry of existence, whether woven by gods, equations, or the explosive rebirth of a singularity. And that's the white hole hypothesis's true gift. Not answers, but a universe more mysterious, more interconnected, and more alive with possibility than we ever dared dream. Science fiction has a knack for taking wild cosmic theories and turning them into breathtaking spectacles, and white holes are no exception. Films like Interstellar flirt with the idea, presenting black holes as gateways to other dimensions, their twisting space-time visualized with groundbreaking accuracy. But flip that concept on its head, and you've got the essence of a white hole, not a devouring abyss, but a radiant, universe-spawning eruption. The movie stops short of showing one, but the seeds are there, hidden in the equations scribbled on Cooper's chalkboard and the Tesseract's mind-bending geometry. Compare that to Doctor Who, where white holes aren't just real, they're whimsical plot devices. In the classic episode The Horns of Nimon, the TARDIS literally gets stuck inside one, treating it like a cosmic traffic jam where time runs backward. It's pure fantasy, of course, but it captures the public's fascination with the idea, a doorway where physics as we know it flips inside out. These portrayals thrive on spectacle, but they also reveal something deeper, how storytelling bends science to explore existential questions. When Event Horizon imagines a ship's warp drive tearing a hole into hell, or Star Trek toys with singularities as power sources, they're not citing peer-reviewed papers. They're asking what if, the same question physicists grapple with, just dressed up with Hollywood explosions. The divide comes down to consequences. In Stargate, traversing a wormhole is as easy as stepping through a shimmering portal. Real science, not so much. Crossing a white hole's threshold, assuming you could find one, would mean confronting energies so violent they'd shred atoms. Fiction glosses over the messy physics. Reality demands we wrestle with quantum gravity and entropy's iron grip. Yet pop culture's greatest service might be priming audiences to expect the universe to be stranger than textbooks suggest. When Contact depicts a wormhole network built by advanced aliens, or Thor, Ragnarok treats black holes as gladiatorial arenas. They normalize ideas that once seemed absurd. White holes haven't gotten their blockbuster moment yet, but when they do, it'll likely hinge on that same blend of awe and artistic license, the irony. Some theories suggest white holes could explain phenomena sci-fi already loves, like gamma-ray bursts or dark energy. Life might not imitate art here, but art could be hinting at truths we're just starting to unravel. What's vital is recognizing where the line blurs. When the Flash name drops white holes as a speedster's power source, that's pure comic book logic. But when physicists like Carlo Rovelli discuss them as quantum gravity's natural endpoints, that's cutting-edge hypothesis. Both matter, one sparks wonder, the other tests it against math and observation. The trick is enjoying the fiction while respecting the fact, because somewhere between Hollywood's white holes and Harvard's whiteboard equations, we might just find the next great leap in understanding the cosmos. After all, today's sci-fi fantasy has a habit of becoming tomorrow's front-page discovery. Who's to say white holes won't be next, so where does this leave us? The white hole hypothesis isn't just a quirky footnote in cosmology. It's a paradigm shift, challenging everything from the Big Bang's singularity to the very nature of time and causality. At its core, it suggests that our universe might not be a one-off event, but the offspring of a black hole's death throws in another reality. Picture that for a moment, every black hole we've ever observed could, in theory, be the seed for an entirely new cosmos, each with its own laws of physics, its own story unfolding in ways we can barely fathom. This idea doesn't just solve cosmic puzzles, it reframes them. The Big Bang's inexplicable singularity, gone, replaced by a quantum bounce where gravity's crushing grip meets a natural limit. The fine-tuning of our universe's constants, no longer a stroke of luck, but the result of an infinite evolutionary chain where only the most stable universes survive long enough to spawn others. Even dark energy's mysterious push could be the lingering echo of our white hole's explosive birth, a cosmic afterburn still propelling galaxies apart. Yet for all its elegance, the white hole hypothesis forces us to confront an even bigger question. Could reality be stranger than science fiction? We're used to black holes as cosmic villains, but what if they're cosmic midwives birthing universes we'll never see? The math allows it, the theories support it, but until we catch a flicker of proof, an anomalous gamma-ray burst, a whisper in gravitational waves, it remains a tantalizing what if. That's where you come in. What's your take? Does the Big Bang still hold the crown, or does the white hole's audacious vision of cosmic rebirth resonate more? Drop your thoughts in the comments. Let's geek out over the wildest ideas shaping our understanding of existence. And if this kind of mind-bending content fuels your curiosity, hit subscribe. We're just getting started. The universe is weird, wonderful, and waiting to be explored together.